Thank you, Professor Tumke. I would like to thank my friends, Professor Shastri and Manoj, who are organizers of this meeting, and I know them for a long time. They have been my colleagues, and I thank Professor Shastri for letting me prepare for this lecture a little bit. So the title is something geometric. I'm not a geometer, but I hit upon it because of a paper of Philip Gilles. I will come to this, but let me begin with some example about what I'm going to talk on. So the example is something all of us know. So let's look at the following group. G is SLN of field K, and let's assume the number of elements in K is at least 4. So then we know from linear algebra, so there are these special matrices, Eij alphas, which are just, so you have ith and jth, ith row, jth column, where they intersect, you have 1, you have alpha, and you have 1s on the diagonal, and here I am assuming I is not j. So these are unipotent matrices, and it's a simple exercise or result in linear algebra, essentially rows and column transformations, which say that the group SLNK is indeed generated by these special elements. So this is also this group is perfect. And simple modulo its center. So this is simple modulo center, which sometimes one calls as projectively simple. So going by this example, a very long time back, I think around maybe early 40s, I am not very sure about the numbers here, Tanaka and Artin wanted to investigate this when you replace a field by a division ring. They hit upon the following conjecture. I will define things in a minute. It says, suppose I have a central simple algebra. Algebra over a field K. I can then talk about the group of elements in A which have reduced norm 1. So I will say, I'll define what is reduced norm, what is a central simple algebra. I think people know, but I'll just say this in a minute. Is this, so the conjecture, or this is equal to the commutator subgroup of the group of units in A. So this is a conjecture. This was a conjecture called Tanaka-Artin conjecture. And these groups are very important if you're studying algebraic groups. These give you what are called classical groups of type A, the simply connected ones. So what is a central simple algebra? So the structure theory, I'm sorry, this suddenly becomes very loud. So there is this theorem of Wedderburn which says that any central simple algebra is of the form matrix algebra with entries in a division algebra D. So everything is over a field K. So such that center of D is K. So these are what are called central simple algebras. And you have the determinant map from the matrix algebra to K. You have the determinant map, and you can, that is the reduced norm. In general, so if you take such an algebra, so D be a central division algebra over K, then one knows by basic algebraic analysis that if I base change to the algebraic closure, then this is a certain matrix algebra. And this tells me that dimension of D is always a square. And this n is defined to be the degree of D. I'm assuming D, this is a division algebra. Is this audible? No, so I will say this, I'll come back to this in a minute. Yeah, this is, you are right, it's not the usual one. So for this situation, if I start with a division algebra, then I have a matrix algebra when I base change. So what I meant was, so you'll take any element x in D and then consider x tensor 1, then it's a matrix, you fix any isomorphism and then take its determinant. So this is an element of K. So this can be shown, and this is what is called reduced norm of. So this is a reduced norm map. I will denote it by ND. So this goes from D to K, and it's multiplicative because of determinant property from K, D star to K star. So this is a homomorphism. And SL1D, by definition, is those elements of D which have norm 1. And because of this, you can see that this is defined by an algebraic equation. So this gives us an algebraic group over the ground field K. So when you base change to K bar, in fact, over a finite Galois extension, you will see that. So I'll use this notation for base change. This is SLN, where N is this N. So going back to Tanaka-Artin, one can easily reduce this conjecture to proving the following. So this is a problem now, more than a conjecture, because this was disproved by Platonov. The question is SL1D equal to the commutator of D star D star? Around 1950, I'm not going to give a survey of this topic because I'm not at all prepared. There are too many numbers to remember, but there is a theorem of Wang which says this: if degree of D is square free. So as I said, we can assume D is a division algebra now. Then indeed SL1D is equal to D star D. However, around 1975, so 25 years later, maybe I should say before this, a conjecture that was proposed by Kneser and Titz. So this was again a conjecture. This is around 1964, which says that if I will define terms which are not defined yet, if G be simple. So when I say simple, I look at the group over K bar. So it's simple in that sense, simply connected. So there are no proper coverings of G. I defined over K, defined and isotropic over K, over a field K, then the group of K rational points of G is generated. So this is equal to Gk plus, which by definition is the subgroup generated by all unipotents in G. So I am being a little sloppy here. I will, so this is not true in general. I will assume K is perfect, then this simple description exists for Gk plus. Otherwise, I have to define what is radical, unipotent, radical, and so on. So this was conjectured, and in 1975, I don't know how far I can go in this direction. So Platonow in 1975 constructed an example of the situation of field K and a division algebra D over K, central division algebra, such that, so this example is a bit involved, so I will skip it right now, such that SL1D is not equal to D star D star. So the conjecture was disproved here. However, as it happens usually, it started a new branch of algebra called reduced K theory. So going by this example, this following invariant was defined. So one defines what is called the Whitehead group of an algebraic group G. So suppose I have an algebraic group G over K connected reductive. And assume it is isotropic over K, so which means that is the K points of G contain unipotents, have or has a non-trivial unipotent. So K isotropic means this. Assume this, define the Whitehead group of G over K. So this is very specific to over K. It makes sense over any extension of K. You can mimic the definition. So this is just the quotient Gk mod Gk dagger. This is a normal subgroup. As you can see, I have taken all unipotents. So you can take the quotient. This is a certain group. Obstruction to this conjecture lies there. And many examples, once you have one counterexample, then you have many. So as I said, the whole branch, new branch of algebra started there. However, so I have to stop at 4 o'clock. Yeah, so then the conjecture was changed to a problem to compute the Whitehead group. You start with an algebraic group and compute this or find out if it is trivial or not. And let me again go back to this example of SLN D. So let's assume n is bigger than equal to 2. So then this is simply connected K isotropic algebraic group, defined over K, of course. N is at not the degree of D or anything, just any N, but at least 2. So you have matrices of size at least 2 by 2. And then if you notice any such matrix, so I have some one entry somewhere, I can join this to the identity matrix using a line segment. So I can define gamma from the affine line to this group G such that gamma of 0 is, let's call this matrix as X, and this is identity matrix. This is X, and gamma at 1 is identity matrix. Just take combination. So instead of alpha, you substitute it by alpha t, which is, so I want it, so it's 1 minus t alpha plus t. So the point I'm trying to make is this new matrix xt, which is obtained by putting alpha t in place of alpha, belongs still in SLN of D, and has this, so this parameter t is now, so this is a morphism of algebraic groups, morphism of algebraic varieties, and has this property. And using this, you can take any element of GK plus, you take any element of GK plus, which is going to be a product of such matrices, and you can connect it to identity by constructing such a morphism. So any element of GK plus can be joined to the identity. So this leads me to the following definition. Which is a bit geometric in nature. So let's take any so X be any algebraic irreducible variety over a field K. Assume that the set of K points is non-empty. So take any 2 points X and Y in Xk. You define them to be what is called R equivalent. So R equivalent. If there exists a sequence of points in Xk such that, and rational maps. So rational maps are not morphisms, they are morphisms defined on open subsets of the variety. Rational maps Fi going from, so though I write A1, it's only defined on a subset here. I demand that this morphism is regular at 2 points, say 0 and 1. So regular at 0 and 1. So defined over K, this morphism should be defined over K. Regular at 0 and 1 such that when I look at Fi at 0, this is, so let me say 1 less than equal to I less than equal to N. So Fi at 0 is Xi minus 1, and Fi at 1 is Xi. So I am able to join X and Y, though not directly by a line segment, but I have piecewise, I can join them by several line segments via a sequence of points. So this is an equivalence relation, and the set of equivalence classes is denoted by Xk over R. So the observation here is, if G is a connected algebraic group over K, you have a special subgroup here, which is denoted by Rg of k. This is all those points in Gk which can be joined to the identity in this manner. So then it can be shown that this is a normal subgroup of the group of k points. You look at the quotient of Gk by this special normal subgroup, then so this is a little theorem due to lots of, I don't know, I will just say Gilles here, but maybe it's not due to him. So I think it's not Gilles. Anyway, let me remove this. So it's not my theorem, that's all, what matters. Gk mod R, there is a natural bijection with Gk mod Rgk. So this set has a natural group structure coming from here. And this is an analog of, so remember I defined this for any variety. So this definition makes for any group. I don't need unipotents to define this. So the theorem of Gilles, which I need to mention here, is which is very recent. In fact, I have it here. So this is in the Bourbaki seminar on Knesertits, which is in 2006-7. So it's called Problem of Knesertits in French, of course. The theorem is that if G is k isotropic, so that means the group of k points has at least one non-trivial k unipotent. Then look at that group I defined there, the Whitehead group, which is Gk mod Gk plus. This is isomorphic to this group, Gk mod R. So I will just use this left-hand side to denote this group. And the point here is, when the group is isotropic, these two are isomorphic, meaning when there are unipotents, either description is fine, but your group may be anisotropic. Then this is a way to look at it. Okay, so because of this result, Knesertits' problem is reduced to computing this. So here is a definition. So we call G R trivial if GL by R is trivial for all extensions, field extensions L of K, all extensions. And again, theorem of Gilles is that, I have not defined retract rationality, but I'll do that, is that if G is simple in the sense I defined, simply connected, K isotropic, then WGL, so this is WGL is trivial for all L over K extensions, is equivalent to saying G is what is called retract K rational. So I will define this term now, K rational, sorry. Before I do that, let me say what is positive about Knesertits. Why was it conjectured in the first place? Yeah. So here is theorem of Platonow. G as in Knesertits hypothesis and K local, a local field. Then Kneser-Tits is true. So over local fields, Kneser-Tits conjecture holds. And the hint or clue came from classical groups. It was first settled for classical groups, and then he did it in general. And present, including this seminar, the present situation is, among other things, so this is a theorem of including several people. So, of course, I don't have time to list all the possible names, but let me start with Chevalier, then Steinberg, including some modern names like Gill, then Garibaldi, and more importantly, these two guys have a large contribution to the problem. Prasad is Gopal Prasad, Raghunathan. So this is not a one paper, this is collection of several papers, and there are some more dots there I'm not filling. Is that if K is a number field or is a global field, then Kneser-Tits conjecture holds. So I mentioned Wang's result, I suppose I've forgotten now. I hope I mentioned, which says that if I have a square-free degree division algebra, then Kneser-Tits or any of these things is true. So let me define what is retract rational. I'm not really an expert on this particular part of what I have written here, but it so happens that these are equivalent. So retract rational just means, so a variety x over k is retract k rational if there exists a open subset U of X, non-empty open subset, such that and some open subset V of some affine space of course it has to be non-empty such that, so when let me draw the picture that is better. So you have U here, you have U again, but then look at V. So this is V. So there exist morphisms in this direction, say F and G, such that the composite is identity. So the identity morphism of U factors through an open subset of affine space. So then you call X retract rational. The stronger notion is rational. So you say X is K rational if X is birational to an affine space. And if G is K rational, then it's easy to see then G is R trivial. Some of examples of this situation include the following. So as I wrote there, all those groups here, these will be rational. Some examples are, for example, spin group of a quadratic form F. So these results are over arbitrary fields. Let's throw away characteristic 2. Take a quadratic form F, which has a non-trivial 0. So it is what is called isotropic over K. Then this is rational. Then any spin, as long as the dimension of the quadratic form is less than or equal to 5. And then so then I will say also any algebraic group, any group G of rank less than or equal to 2. So rank has some meaning which I don't want to go into. I will have to say it roughly to say my theorem. Yeah. So the theorem I have is the following. So before I go into that, let me define construct one particular group here. So let's consider a vector space. So I'll just say here uh, some groups of of type E6. So one particular, so I'll tell you how to construct simply connected E6, which many of you know, I'm sure. So let's take V equal to the matrix algebra, 3 by 3 matrix algebra, 3 copies. So fix your field K and look at 3 copies of the matrix algebra. Then I have a very nice cubic form defined on K. So which is defined as, suppose I take a triple of matrices. I should apologize, I have given part of this talk in the earlier meeting that was held in HRI in Allahabad. So this work is continuation of that and there will be yet one more. So you'll hear me again sometime. So this is defined as determinant of X plus determinant of Y plus determinant of Z minus trace of XYZ. So if you look at this cubic form and look at the look at the group of so you look at the subgroup of GLV, which consists of all those maps which preserve N. Look at those guys which preserve N. Then this, maybe I written it the wrong way. I should say, this is then H is the split simply connected E6 defined over K. Let me define a twisted version of this group. So as I said, this group is split. So the other extreme, for the other construction, you fix a degree 3 central division algebra over K. It may or may not exist, but assume it exists. And fix a scalar mu, which is not a reduced norm from D. So again, this may or may not happen. So these are arithmetic conditions on the field. If such a condition happens, then you can construct the following space. V to be, you take 3 copies of D, and then you define the form N on a triple ABC as the reduced norm of A plus mu times reduced norm of B plus mu inverse times the reduced norm of C, and then you subtract the reduced trace of ABC. So reduced trace is the trace of any element when you go to some splitting field of D. And then you look at the group of isometries of this form. That is going to be, so this gives you, so isometry group of N H is this. So this is anisotropic. Simply connected. Simple of type E6 defined over K. It's not known if all E6 look like this, but one can characterize which E6 look like this, what are called strongly inner twists of the split E6. So let me mention my result. Let me draw some pictures here of Dinkin diagrams, which will be, the result is about those. So this is the group I have drawn here, written down there. So this has no circles on it. Then there is E7, which has rank 1, and it's built up from this. And this node of E7 is circled. So, and then there is an E8, which has rank 2, and there is a number here. I'll explain what that is. So both these end nodes are circled. So the common part is this part. All these groups contain the E6 I wrote down there. And the property, so this is not the most general version of E6. You can do a quadratic extension and repeat this construction. So, however, the fact is that the E6 I wrote here, so the theorem is H here is split over a cubic extension of K. So as long as these, so this 78 is the dimension of that group E6. These are groups of type E7 and E8, which contain this E6 as what are called what is called its anisotropic kernel. So as long as, and one knows that anisotropic kernel of these groups arises always like this, using such algebraic construction, then the theorem is then H is R trivial. And therefore, corollary is if G has what is called Tits index as E7871 or E7882 split over a cubic extension. So one knows that these groups always split over a degree 6 extension. So assume it is splitting over a cubic extension, then G is R trivial. I forgot to mention one important connection with group theory here, which should interest people interested in simple groups, is a theorem of Tits, which says that, this is a very old theorem, says that, so if G is as in the Kneser-Tits hypothesis, then you look at the group, the subgroup of GK, which was generated by K unipotents. So this is projectively simple. So as an abstract group, this is simple. When I say an algebraic group is simple, even SLN, for example, it's not simple. It has a center, which is normal subgroup. So you have to mod out by that, then you get an abstract simple group. So this group has that property. And Kneser-Tits, if it holds, the truth of Kneser-Tits, so holds, implies GK is projectively simple. And what this result therefore will give us is, if I take G as any of this and take any extension of K, then the group of K points is simple. So I stop here. No, no problem. I got, my nerves are broken now.